Today we're going to be doing October-November 2023 paper 51. So that's paper 5 variant 1. Question number 1 says the concentration of dissolved oxygen in a sample of water can be measured using the following method. So that's your objective, right? You want to find the concentration of dissolved oxygen, okay, in a sample of water. Manganese 2 hydroxide is oxidized by oxygen dissolved in a sample of water to form manganese 3 hydroxide. Okay, so you have some oxygen dissolved, it can oxidize the manganese 2 to manganese 3. The manganese 3 hydroxide then reacts with iodide ions to produce aqueous iodine. So that's the second equation shown, right? The manganese 3 hydroxide is reacting with iodide to give you iodine. The amount of iodine produced is proportional to the amount of dissolved oxygen. 25 cm cube of the solution containing aqueous iodine is transferred into a conical flask and titrated against 1 into 10 to the power minus 3 moles per dm cube sodium thiosulfate. So what we do is we take the iodine that was produced here, and we titrate it against 1 into 10 to the power minus 3 moles per dm cube sodium thiosulfate. Okay, we titrate the iodine against the sodium thiosulfate. Complete table 1.1 and determine the mean titer to be used in calculating the concentration of dissolved oxygen. So for the titer value, we're going to take the final minus the initial. So here we get 27.30. Here we get 27.00. We get 26.70 and then 26.80. Okay. Make sure you write down all the titer values to 2 decimal places. So for the mean titer, we have to use concordant values, right? These two values are concordant. That means they're within 0.1 cm cube of each other. So your mean titer is just 26.7 plus 26.8 divided by 2. And that gives you 26.75 centimeter cube. Okay, 26.75 cm cube. Calculate the concentration of dissolved oxygen in the 25 cm cube of solution. So you're working. So now in this titration, right, we titrated the iodine that was produced against sodium thiosulfate. So this mean titer is the volume of sodium thiosulfate used because iodine was titrated against the sodium thiosulfate. That's what we had in the burette. So the first thing we're going to do is we're going to find the moles of sodium thiosulfate. Okay, for sodium thiosulfate, the concentration is given to us as 1 into 10 to the power of minus 3 moles per dm cube. Okay, so that's 0.001 moles per dm cube. Okay, and the volume is 26.75 centimeter cube. Right, that's the mean titer. So the number of moles is concentration times volume is 0.001 times 26.75 divided by 1000. That gives us 2.675 into 10 to the power of minus 5 moles. Okay, that's the number of moles of sodium thiosulfate. Right, again, the concentration is given to us as 0.001 moles per dm cube, and we have the mean titer. Now we can figure out the amount of iodine that was produced. Okay, the amount of iodine that was produced in this reaction. Okay, the number of moles of iodine will be half the number of moles of sodium thiosulfate, right? So it's a 1 to 2 ratio. For every 1 mole of iodine, we need 2 moles of sodium thiosulfate. Number of moles of iodine, right? Number of moles of iodine is equal to 2.675 into 10 to the power minus 5 divided by 2. So that gives us 1.3375 into 10 to the power of minus 5 moles. Into 10 to the power of minus 5 moles. So now we have the moles of iodine. Okay, we have the moles of iodine. That's 1.3375 into 10 to the power of minus 5 moles. Right? That's the number of moles of iodine. Now we want to find how much oxygen we had. Here. Okay. We know that this manganese 3 hydroxide was produced in the reaction of oxygen with manganese 2 hydroxide, and then we know that manganese 3 hydroxide reacted here to produce iodine. So we know the number of moles of manganese 3 hydroxide is 2 times the number of moles of iodine, right? Because there's a 2 to 1 ratio here. For every 2 moles of manganese 3 hydroxide, we have 1 mole of iodine. So the number of moles of MnOH3 is 2 times the number of moles of iodine, right? The number of moles of MnOH3 is 2 times the number of moles of iodine. And that means that the number of moles of oxygen the number of moles of oxygen is 1/4 the number of moles of manganese 3 hydroxide, because for every 4 mole of MnOH3 produced, 1 mole of oxygen is reacting. The number of moles of oxygen is 2 times the number of moles of iodine divided by 4, right? Number of moles of MnOH3 divided by 4. So that's just the number of moles of iodine divided by 2. That's just the number of moles of iodine divided by 2. So we can say that the number of moles of oxygen, okay, number of moles of oxygen is the number of moles of iodine divided by 2. Okay, and that gives us the number of moles of oxygen as 6.6875 into 10 to the power of minus 6. So that's the number of moles of oxygen. We want to find the concentration of oxygen, which is just the number of moles divided by the volume. So that's 6.6875 into 10 to the power minus 6. That's the number of moles divided by the volume. The volume here is 25 cm cube. So that would be 0.025 decimeter cube, right? That's 25 divided by 1000. So that gives us the concentration of oxygen as 2.675 into 10 to the power minus 4. 2.675 into 10 to the power minus 4 moles per decimeter cube. Suggest a suitable apparatus for the transfer of 25 cm cube of the solution containing aqueous iodine. That would just be a 25 cm cube volumetric pipette. Okay, 25 cm cube volumetric pipette. Water samples are collected in full sealed flasks. Explain why the sealed flask must be completely full. Now these water samples, right, these water samples contain manganese 2 hydroxide. Okay, they contain manganese 2 hydroxide, and we know that manganese 2 hydroxide can react with oxygen, right? So when we want to do this experiment, right, we're using manganese 2 hydroxide to determine the amount of oxygen dissolved in the water, right, dissolved in the water. Now if this flask was not full, right, if this flask was not full, right, let's say the level of water was somewhere over here, right, so the flask was not full, then what would happen is that we have oxygen in the air, right? And that oxygen in the air may also react with the manganese 2 hydroxide. We don't want that to happen. We want the manganese 2 hydroxide to only react with the oxygen dissolved in water, right? So we don't want any air in the flask, okay? We don't want any air in the flask because air will also contain oxygen. That would give us an inaccurate value for the amount of oxygen, right? Because we also have oxygen from air then. If the flask is completely full, there's no trapped air, so there's no oxygen from the air that reacts. Only the oxygen in the water will react, okay? Only the oxygen in the water will react. So the reason this is done is to ensure that oxygen from the air, okay, oxygen from the air does not react. So it does not react with manganese 2 hydroxide. The concentration of oxygen in water at different temperatures is shown in table 1.2. The concentration value is missing for 25 degrees Celsius. Plot a graph of concentration of oxygen on the y-axis against temperature on the grid. Use a cross to plot each data point. Draw a smooth curve of best fit. So here I've drawn a smooth curve of best fit. Okay, I've drawn a smooth curve of best fit over here. Part 2 says use the graph to deduce the concentration of oxygen at 25 degrees Celsius. Okay, I've clearly shown my working here. You can determine the concentration of oxygen at 25 degrees Celsius. Okay, I get 2.55 into 10 to the power minus 4. Okay. Each small square is 0.05. Okay. Each small square is 0.05. Right? Because 10 squares is 0.5. 10 small squares is 0.5. So here I get the concentration of oxygen as 2.55 into 10 to the power of minus 4 moles per decimeter cube. Okay, your value may be slightly off, but that's okay. Circle the most anomalous point on the graph. Suggest an explanation for this anomaly. Assume that there was no error in measuring the oxygen concentration. So here we have the anomalous point, right? We have the anomalous point here. And the question says that assume that there's no error in measuring the oxygen concentration, which means that there must have been some mistake we made when we were recording the temperature. Okay, there must have been some mistake in recording the temperature because there's no mistake been made when determining the concentration of oxygen. Now, this particular concentration of oxygen, right? This particular concentration of oxygen, okay, it basically corresponds to a greater temperature. It corresponds to a greater temperature, right? This is a temperature of roughly 13.5 degrees Celsius, right? 13.5 degrees Celsius. So the actual temperature was roughly 13.5 degrees Celsius, right? That's what would give you this particular concentration of oxygen. This point should lie somewhere here. Now again, because there's no mistake been made in determining the concentration of oxygen, this concentration of oxygen is determined correctly. So it should lie somewhere here. It should correspond to a temperature of around 13.5 degrees Celsius, right? So the actual temperature was 13.5, but the recorded temperature is 10 degrees Celsius, right? The recorded temperature is 10 degrees Celsius. So here we will say that the actual temperature, okay, the actual temperature is greater, okay, is greater than the recorded temperature, okay, than the recorded temperature. So here we have question number 2, which says benzene diazonium chloride decomposes in water as shown in the following equation. A solution of 0.075 mole per dm cube benzene diazonium chloride decomposes at a constant temperature of 50 degrees Celsius. The volume of nitrogen gas collected is recorded every 5 minutes for 45 minutes. Draw a labeled diagram to show how the apparatus could be set up to carry out this experiment. So here we want to collect and record the volume of nitrogen gas every 5 minutes. So for that we're going to need a graduated gas syringe, and we also want to maintain a temperature of 50 degrees Celsius. Okay, so for that we're going to use a water bath. Okay, we're going to use a water bath, a thermostatically controlled water bath. So here, okay, we have a flask. Okay, you can draw a side-on flask like this. So this is a side-on flask. This is connected to your gas syringe. This is connected to your gas syringe. So draw the gas syringe here. This is a graduated gas syringe. This. So the graduation marks as well. This. And then since we want to maintain a constant temperature, right, we're going to need a water bath. So you can use a stand. So you can use a stand. You can use a stand to suspend the flask in a thermostatically controlled water bath. And of course, the flask should be sealed. And then here you have the contents of the flask. Right? The contents of the flask should be completely submerged in the water bath, right? To ensure that the temperature is uniform, 50 degrees Celsius. Now we're going to label the apparatus. So we have a graduated gas syringe. Okay. We have a temperature controlled or thermostatically controlled water bath. We have the contents of the flask, that's C6H5N2, this plus H2O, right, liquid. And we have a stand to suspend the flask. And then this is a sidearm flask, okay, a sidearm flask, and this is a rubber band, right? So you don't have to label that here. So using this method, the student obtains the graph shown in figure 2.1. Okay, so this was the graph that was given to us. Okay, this is the graph that's given to us, this curve over here. Okay, on figure 2.1, draw a tangent to the curve at t is equal to 0 minutes. Calculate the initial rate of reaction in centimeter cube per minute. Okay, so we need to draw a tangent to the curve at t is equal to 0, right? And we want to find the slope of that tangent. To get the rate of the reaction at t is equal to 0, right? That's the initial rate of the reaction. Now it may be helpful to extend the curve a bit below, okay, a bit below the origin or below the x-axis here, okay? Make it easier to draw the tangent, okay? Although they are very lenient, in terms of like the range of values that they'll accept for the gradient. Okay, once you draw the tangent, you can just label the points that you've used. Okay, drawing these construction lines. So I've used the point 10, 56. Okay, 10, 56 right here. So that's this point. And then I've also used the point 3.5, 20. Okay, 3.5. So these are the points that I've used. I want to find the rate in centimeter cube per minute. That'll just be the change in volume that's on the y-axis, okay, over the change in time. So that would be 56 minus 20 divided by 10 minus 3.5. Okay, and that gives us 5.54 centimeter cube per minute. Okay, 5.54 centimeter cube per minute. Explain why the initial rate of reaction is calculated at t is equal to 0 minutes rather than dividing the total volume of gas produced by the time taken to produce it. So if you took the total volume of gas and divided it by the time taken to produce it, what would you get? Well, then you get the average or the mean rate of the reaction, right? So this would give the average or the mean rate of the reaction. Okay? The average or mean rate of reaction rather than the initial rate. Okay? Describe how the curve in figure 2.1 would be different, if at all, if the atmospheric pressure increases. All other conditions stay the same. Now over here, if the atmospheric pressure would increase, in other words, we're increasing the pressure, right? In this particular reaction, you don't have gases in the reactants. You don't have gases in the reactants. So it would not affect the rate of a reaction, right? It would not affect the rate of the reaction. If you had a gas in the reactants, it would also increase the rate. But here the rate will not be affected by the atmospheric pressure. However, since you're collecting a gas, if you increase the pressure, the volume of gas decreases, right? Because pressure is inversely proportional to volume. Okay, for gases, pressure is inversely proportional to the volume of a gas. So if you increase the pressure, the volume of gas collected would decrease. Now, if the volume of gas collected would decrease, that would mean that the curve you obtain, right, will be below the curve that was shown in this graph. Okay, that would be below this curve over here, right? Because again, pressure increase means that you get a lower volume of gas. Okay, you get a lower volume of gas for a given number of moles. So we're going to talk about how the curve would be different, right? So the curve would be below, okay, the curve shown. Okay, the curve would be below the curve shown. Okay, and the reason why is because as pressure increases, right? So as pressure increases, okay, the volume of gas collected decreases. Okay, volume of gas decreases. I've written that in parentheses because they're not asking for an explanation. They're only asking for a description of how the curve would change. Okay, they only want a description of how the curve would change. However, I still mentioned the reason in parentheses here. On figure 2.1, draw a second curve to show the graph produced of the same volume of 0.0375 moles per dm cube of the diazonium salt decomposes at a constant temperature of 50 degrees Celsius. All other conditions stay the same. Now, initially you had used 0.0750 moles per dm cube. So you've decreased the concentration by a factor of 2. Okay, you've halved the concentration. You've halved the concentration, okay, or decreased it by a factor of 2. Okay, you have the same volume. Of the diazonium salt. So that means what you've done here is you've decreased the concentration. Okay, the volume is the same, which means your number of moles has also decreased by a factor of 2, right? The number of moles has decreased by a factor of 2. So you have half the number of moles of diazonium chloride, which means that the volume of gas collected will also be half. Okay, the volume of gas will also be half. So you have half the volume of gas being collected, and the rate of the reaction will also decrease. The rate of the reaction will decrease because you're using a lower concentration of the diazonium salt. So now, instead of collecting 55 cm cube, we're going to collect half the volume of gas. Okay, so this curve should plateau at 27.5 cm. Okay, at 27.5 cm cube. Half the volume of gas, because you have half the number of moles of the reactant. Okay, and the graph would be less steep, right? The graph would be less steep because decreasing the concentration will result in a decrease in the rate of the reaction. Another student investigates the effect of changing the concentration of the diazonium salt at 50 degrees Celsius. He measures the time taken to collect 0.015 decimeter cube of nitrogen gas and calculates the rate of nitrogen production by dividing 0.015 by the time taken. So that will give you the rate in decimeter cube per second. The results are shown in table 2.1. Okay, so here we're collecting 0.015 dm cube. Again, they've given us the time in seconds. We want to complete the table to calculate the values for the rate of nitrogen production, giving our answers to three significant figures. So we take the volume, right, that's 0.015, and then we divide it by the time taken. Okay, and we get the rate. We get the rate of production in decimeter cube per second to three significant figures. So it's pretty straightforward. However, again, be careful when you're noting down these values. Okay, any errors in rounding, result in 0 marks for this column. Okay, so this entire column is for 1 mark. Just be careful when you're rounding. You don't have to write in standard form, okay, because the question isn't really asking for that, but you can. There's no issue with that. The reaction is first order and obeys the following rate equation. It's first order with respect to the concentration of diazonium chloride. Okay, it's first order with respect to the diazonium chloride. Explain how the data in table 2.1 supports this statement. Now, since the reaction is order 1 with respect to the diazonium chloride, right, since the reaction is order 1 with respect to benzene diazonium chloride, that's the diazonium salt here, it means that the rate is directly proportional to the concentration. Okay, we go back to the table and we can see that if we look at these two experiments, right, we can see that here I'm doubling the concentration, and I want to see what effect that has on the rate, right? I want to see what effect that has on the rate. So I can say, so here I can say that if I double the concentration, I can say that if I double the concentration from 0.100 to 0.200, right, the rate goes from 1.23 into 10 to the power of minus 4 to 2.34. Okay? 1.23 into 10 to the power of minus 4 to 2.34. All right. So what I'm doing is I'm doubling the concentration. Okay, I'm doubling the concentration, and the rate is changing by a factor of 2.34 divided by 1.23. 2.34 divided by 1.23. So it's changing by a factor of 1.9. Okay, it's changing by a factor of 1.9, which is roughly the same, right? Doubling the concentration results in a rate also doubling. So therefore, we can say that it's first order, here order 1, with respect to the diazonium chloride, okay, the benzene diazonium chloride. State the dependent variable in this investigation. So in this particular investigation, okay, the student is varying the concentration. Right, and the time taken depends on the concentration of the diazonium salt. So the time taken to collect the nitrogen gas depends on the concentration of the diazonium salt. So the dependent variable here is the time taken. Okay? The time taken to collect the nitrogen gas. Okay, to collect the 0.015 decimeter cube of nitrogen gas. The student wants to perform a similar experiment using 0.2 moles per dm cube benzene diazonium chloride. Describe how the student should make a standard solution of 100 cm cube of 0.2 mole per dm cube diazonium chloride starting from a solution of 0.5 mole per dm cube of the diazonium salt. Give the name and size of any key apparatus which should be used and describe how the student should ensure that the volume is exactly 100 cm cube. Write your answer using a series of numbered steps. So you're starting out with a 0.5 mole per dm cube solution. Okay, you want to make a 0.2 mole per dm cube solution. So this is a dilution, right? This is a dilution. You want to make a 100 cm cube solution, so we're going to use a volumetric flask, right? But first, we need to figure out how much we need of the concentrated solution. For a dilution, we can say C1V1 is equal to C2V2, right? The initial concentration is 0.5 mole per dm cube. We don't know the initial volume that we need, so that will be V1. The final solution that we want has a concentration of 0.2. The final volume that we want is 100 cm cube. Okay, again, you don't need to convert to dm cube. Okay, you don't need to convert to dm cube because we're just taking the ratio. Okay, so here we'll get our initial volume as 40 centimeter cube. Where our initial volume is 40 centimeter cube. So what we're first going to do is we're going to transfer 40 cm cube. So what we're first going to do is we're going to transfer 40 cm cube, okay, of the 0.5 mole per dm cube, 0.5 mole per dm cube solution of C6H5N2Cl, okay, using a burette, into a 100 cm cube volumetric flask, okay, 100 cm cube volumetric flask, okay, and then we're going to make up to the mark. With distilled water. Okay. So make up to the mark with distilled water. The 100 cm cube mark with distilled water. And then we're going to invert the contents of the flask, right? Invert the contents, right, to mix. Okay. Explain why step 4 must be carried out at a temperature below 5 degrees Celsius. We know that diazonium salts are heat sensitive, right? Benzene diazonium chloride undergoes hydrolysis with water, right? At a temperature of above 5 degrees Celsius. So they're very unstable. Okay, it reacts readily with water at room temperature even, okay, or if you allow the temperature to go above 5 degrees Celsius. The reason this is done is to ensure, okay, that the C6H5N2Cl, right, benzene diazonium chloride, does not undergo hydrolysis, right? Does not undergo hydrolysis. Because if it reacted with water, right, that would result in a decrease, okay? That would result in a decrease in concentration, resulting in a decrease in the concentration. Okay, we don't want that because that would affect our readings. C6H5N2Cl is used in the manufacture of synthetic dyes. The student prepares a sample of the dye using the reaction scheme shown in figure 2.2. So in step 1, phenylamine is converted to the diazonium chloride. Right, again, this is carried out at a temperature below 5 degrees Celsius. And you have to maintain this low temperature when you're making the dye. Right, this is an azo dye. Right, this is the azo group that's responsible for the color of the dye. Okay, so you want to maintain this low temperature because if you don't, then this diazonium salt will react with water, right? The student's final yield was 52%. They had not spilled any reagents or products. Suggest 2 reasons why the student's yield was lower than 100%. Assume no errors were made in the measurement of any substances. So first the student made the diazonium chloride, the benzene diazonium chloride from phenylamine, and then he converted that benzene diazonium chloride to an azo dye, right, by reacting it with phenylamine to obtain the final product, right, which is the solid dye. Okay, so we're producing a solid dye here. Now again, as I just mentioned, right, if you allow the temperature to go above 5 degrees Celsius, okay, the benzene diazonium chloride will undergo hydrolysis. Okay, so one of the reasons why you get a lower yield is because the benzene diazonium chloride, okay, the benzene diazonium chloride is hydrolyzed. Okay, benzene diazonium chloride undergoes hydrolysis. Okay, so the reason it undergoes hydrolysis is because the temperature was not maintained, right? So you could also write that the temperature was not maintained, okay, at below 5 degrees Celsius, to below 5 degrees Celsius, which would result in the hydrolysis of the benzene diazonium chloride. And then this solid dye is obtained through filtration, right? Solid dye is obtained through filtration. So one possibility is that some of the dye remains dissolved in solution, right? So some of the dye, okay, some of the dye remains in solution, okay, remains in solution rather than precipitating, okay, rather than being obtained as a solid, and therefore a lower mass, okay, lower mass of solid is obtained. Okay, lower mass of solid is obtained. Okay, so remains in solution. By remains in solution, we mean it remains in the filtrate, right? It remains in solution, remains in the filtrate, so it's not obtained. It's not obtained through filtration. Explain why the solid dye should be dried before assessing the melting point. Now, of course, if water was present, right, water is an impurity, right? We know that in order to determine the melting point accurately, we need a pure substance, right? We need a pure substance. So, the water here is an impurity, right? The water is an impurity, and therefore the melting point obtained would be inaccurate, right? Melting point obtained would be inaccurate. Okay? Would be inaccurate in the presence of water.